again to my lecture today. Of course, today I'm actually um, going to start a new topic, which I call logistic regression. Can you confirm if you are seeing what I'm projecting right now? Can you confirm that?
I can see it.
Okay, thank you so much. Uh, you know, at the beginning of the semester, we started what we call linear regression, and of course, the linear regression is a situation where type of regression where we are assuming that relationship among variables is can be represented by a straight line in such a way that we can actually predict a variable called response from predictors. Okay, but you know what? The difference between the linear regression and the logistic regression we want to start today is the nature of the response variable. I'm going to say that again. So what determines whether we're going to use logistic regression or we're going to use linear regression, that depends on the nature of the response variable. When the response variable is continuous, I'm going to say that again. When the response variable is continuous, we're actually going to use linear regression. But what if in a situation where the response variable is categorical? Okay, so when the response variable is categorical, then we can no longer use linear regression. So today, the focus is actually going to be how can we fit a relationship between a categorical response variable and predictors. Okay, so that is the focus today. Okay, um, so I'm gonna call that part one. Okay. Now, before we go into the logistic regression proper, I will first want to, you know, I want to walk you through what I call odds versus probability because we're actually going to use this in logistic regression. So understanding of odds, okay, and probability, okay, will enable us to have the understanding of logistic regression. Now let's talk about odds. What do we mean by odds? You know, odds is a ratio of probability of success or to the probability of failure. Of course, success and failure are mutually exclusive, and because of that, one minus probability of success is the same thing as failure. It's the same thing as probability of failure because since success and failures are mutually exclusive, the probability of success plus the probability of failure is going to be equal to one. Okay, so which means here we have um, two uh, characteristics of interest that are actually negating, okay, success, fail, and failure. So by odds, we're talking about the ratio of that of the probability of success to the probability of failure. That's what I'm talking about right here. Okay, and we have a question right here. There's a 50% chance, okay, that we have snow this weekend. Okay, um, this is just a question. I'm not talking about having a real snow this time around. I'm just talking about just a question here. Okay. Okay, so if there is a 50% chance that we have having a snow this weekend, what is the odds of having snow this weekend? Okay, so if you want to figure out the odd, okay, uh, 50% chance, what that actually means, okay, is that the probability of getting the snow is actually going to be 0.5, and the probability of not getting the snow is also going to be 0.5. And in that situation, if you find a ratio of that, I'm afraid that is going to give you 1. Okay, so which means it is kind of dicey. Okay, it's kind of dicey. Okay, guys, confirm again. If you guys are still hearing me clearly.
Yep.
Okay, thank you so much. Now, when you take a look at the second question right here, before I go to the second question situation where odd ratio equal to 1, and what that implies is that the probability of success is the same thing as the probability of failure. So which means there is no anyone that dominates. So you understand now? But if you look at the example 2, the odds of the Vikings, the Vikings, I think it's a football club in Minnesota. Okay, the odds of the Vikings winning the next game is 3-1. Okay, look at that. The odd ratio now, this is 3-1. What is the probability of the Viking losing the next game? So if you want to know the probability of the Viking losing the next game, if you look at this is 3-1. If you add 3-1, that's going to be 4. Okay, so if the totality is 4, so 1 divided by 4, okay, is going to be 0.25. So which means the probability of Viking losing is is 0.25. If the odds of Viking winning, because the way it's going to be when you are trying to talk about odd, you actually give me 1 second. I'm going to connect my iPad right now so that you'll be able to give me 1 second. uh give me 1 second. Okay, thank you so much. Now because when we talk about odd, okay, you actually the you're gonna have the probability of winning. Give me 1 second. The probability of winning. Okay, the probability of winning divided by the probability of losing. Okay, now if that is odd, okay, right now it is ratio 3-1. Okay, it is the if the odd ratio is 3-1, then if I really want to find the probability, okay, of winning, okay, so the probability of winning is actually going to be 3/4. Okay, 3 out of 4, that would be 0.75. And the probability of losing, okay, is going to be 0.25. Okay, so take a look at that. And initially, so if you have 0.75 to 0.25, okay, that was what gave us 3-1. Okay, that they talk about. So I just wanted to see the relationship between the odd ratio and probability. Okay, now um let's go into the detail of logistic regression right now. But because before we go into that, it's better we look at problem that could lead to applying logistical regression. Okay, so let's get started. The story of the space shuttle challenger. If you look at what I'm trying to show you right now, Okay, on January 28, 1986, our space shuttle Challenger explode shortly after takeoff. Okay, it explode shortly after takeoff. Okay, now this is not a success at all. This is not good. Okay, now the investigation discovered that a component in the rocket's collar ring was ruptured and resulted in the explosion. Okay, that was the investigation. That was the result of the investigation, you know, conducted. Okay, now because of that, uh, we want to look at the relationship between O-ring damage and temperature. Okay, because the investigation actually discovered that the component of that was actually ruptured. Okay, and we want to know what was the role of temperature in that. Okay, so because of that, we're trying to look at, or can we have a way to characterize relationship between, O-ring damage and temperature. Okay, and because of that, we have data collected, April 1981. Okay, when the temperature was 66, damage equal to zero. This is my response variable right now. Okay, this is the response. Okay, and this is the predictor. Okay, the temperature is the predictor, the damage is the response, and if damage equal to 1, we mean that omega is damaged. When it is equal to 0, then it means it is not. Okay, so you can see the response is being coded as 0 and 1. This is different from dummy regression. You know what we did in the dummy regression? Okay, where the nature of the predictor was categorized as but this time around, it is the response that we are actually categorizing. Okay, did you see that now? Okay, so we collected data from April 1981. Okay, until we get to probably February or 1984. Okay, so and we plotted this. If you plot this right now, what did you notice? Like the if you the reason why you cannot assume a straight line is because the straight line is going to go over the range of 0 to 1. Okay, the straight line is going to go over the range of 0 to 1, and you know what, the response need to be bounded in the range of 0 to 1, and fitting a linear regression will not actually capture the relationship. Okay, as you can see right here. Okay, and that was why I said, what potential issue do you see when you fit a linear regression model to this data? I want to tell you that people have tried that before. We call that linear probability model. When they fitted linear regression to situation where the response variable is categorical. Of course, the straight line was not able to capture that because the prediction we actually go over the range of 0 to 1, and if the prediction should go over the range of 0 to 1, that will not make any sense at all. Okay, that will not make any sense at all. So, and that was why I said, what is the range of the fitted y? The range of the fitted y should be between 0 and 1, but when you fit a linear regression model, it's going to go over that. Okay, and that was why I said the fitted y could be greater than 1 or less than 0, which doesn't make sense. It doesn't make sense when you fit a linear regression model to that. So another question that I want to ask, does the model satisfy the linear regression assumption?
No, it
Of
doesn't.
Exactly. So it does not, because thank you so much for sharing. How are we going to know whether it's satisfied or not? So what we're going to do, we can actually, you know, uh, obtain the diagnostic plots after fitting the linear regression, and you're going to see that there's going to be violations of assumptions. Number one, if you try to look, if you look at the residual plot, of course, you're going to see there's a pattern, what? And you can see the normal KK plot, there's a violation of normality. I want to tell you, if you make an attempt to fit a linear regression model to categorical response variable, you're going to see that most of the assumptions will actually be violated. And when assumptions are violated, of course, we cannot rely on the model. Okay, so look at that. I also say, according to the diagnostic plot, normality and linearity are violated. Even the equal variance is questionable. Okay, so that is the reason. So those are the things that we're actually going to see. Okay, that made us to actually conclude that one cannot use a linear regression model for situation where the response variable is categorical. So, and you know what? In simple linear regression that we've been doing, of course, we assume that y, given x, okay, we follow a normal distribution with mean of this and the variance of that. Okay, so we made this assumption because the fact, because the nature of the response is continuous, and don't forget that normal distribution is a probability distribution for a continuous random variable. Okay, I'm going to say that again. A normal distribution is a probability distribution of a continuous random variable. And you know what, we made that assumption in the simple linear regression because we realize that the nature of the response variable in the simple linear regression was continuous. Okay, and that was why we imposed normality. Okay, on that. But situation whereby we have a binary response variable, we don't expect the distribution of the response variable to be normal anymore. Okay, because like the current situation in the current example where we are talking about whether the ring will be damaged or not, it means we have two possible nature for the response. Okay, we got two possible nature for the response. Okay, so therefore, because you got two possible nature, the distribution of that is actually going to be Bernoulli. Okay, let me tell you, when we say Bernoulli probability distribution is actually a probability distribution of a discrete random variable. I'm going to say that again. Bernoulli is a probability distribution of a discrete random variable, and of course, when the nature of that of a random variable is dichotomous. Dichotomous means it can actually take two possible nature, and of course, our response variable is going to take two possible nature, and therefore there's going to be this assumption. Okay, now that we know it's Bernoulli, okay, so let's now focus on Bernoulli random variable. Okay, we want to focus on Bernoulli random variable right now. Okay, so if a random variable W, okay, follows a Bernoulli distribution, okay, we're going to have a parameter theta, and the theta is actually going to be the probability of sources, because I know if a variable is categorical, okay, which has published success and failure, I know what we're going to be looking for is the probability of sources. Okay, so the probability of success is actually theta. Okay, so the mean, we may want to know what is the mean and what is the variance of of the W. Okay, so what is the mean and what is the variance? Of course, the mean is actually theta and the variance is theta into 1 minus theta. So this has already been proved in literature. Okay, now how can we now use their knowledge here? Okay, how can we use the knowledge here on a particular a random variable x, I mean y, okay, that is depending on a predictor, okay, and such a way that that very random variable, random variable is actually categorical. Okay, now what is going to be the mean of y given x in that situation where when we're talking about our response here is now categorical. Of course, what we're going to say, since we know that the mean of any categorical random variable, okay, is actually theta, then we're going to say for any given values of x, or for any given predictor, or the mean of y, the mean of a response variable that is categorical is going to be theta x. Okay, so where theta s is now going to be the probability of success at that particular values of x. Okay, and that if that's occur, then it means if I want to find the variance, okay, if I want to find the variance of y given x, okay, then it means if using this using this right now, then I'm also going to have this. So which means our variance will change. It means our variance now depends on the particular values of predictor. Okay, and don't forget that when we're dealing with the simple linear regression, okay, the assumption is that our variance is constant. Take a look at that. Okay, there's an assumption of constant variance, but in the case of a situation where we have where the response is actually categorical, then we don't expect variance to be constant, because and that was why I said the variance of y, okay, given the predict values of a predictor is actually going to change when x takes on different value. Okay, so which means that is one of the reasons why you cannot use a linear regression, okay, for a situation where the response variable is categorical, because there's always going to be a violation of constant variance. Okay, there's always going to be violation of constant variance, and that's exactly what I'm trying to showcase to you right now. Now, if there's a violation of constant variance, and if the range of the response variable is actually going to go over 0 and 1, which is not going to make sense, then what kind of regression are we going to use for situation whereby the response variable is actually categorical? Then we're actually going to use uh, logistic regression. But you know what? What is the origin of logistic regression? I'm actually going to derive that for you right now. Okay, so I want to say logistic regression actually comes from linear regression. So when the response variable is categorical and we can no longer use linear regression, then it means we need to modify linear regression so that we're going to have a new form of regression that can actually handle categorical response variable. Now take a look at this right now. Okay, this is expected value of y, okay, given x, okay, which is equal to beta naught plus beta 1x. That is actually coming from linear regression, right? Okay, now since we know, so what we're going to do here now is we only need to introduce what I call hard. Take a look at this guy here. The other time when I started, I talk about hard, and of course, when the response variable is categorical, we can talk about hard ratio. Okay, we can actually talk about odds ratio, which is the ratio of the probability of success, okay, to the probability of failure. Okay, so if that is the case, so what we actually going to do is this. So what is the probability? I told you the other time that the expected value of y giving x equal to that, okay, is the same thing as theta, okay, and where theta is the probability of success. Now, if that is the probability of success, then what is the probability of failure then? That the probability of failure is actually going to be 1 minus, okay, expected value of y giving x equal to that. So which is the same thing as 1 minus theta, which is also the same thing as 1 minus p. Okay. Now, if I want to do the ratio of p to 1 over to 1 minus p, which is going that's going to be called odd ratio. So which means what I'm actually going to do, okay, is going to use this guy divided by this guy. And when I do that, I'm going to introduce a log. Okay, I'm going to introduce a log, because when I introduce a log, log transform of the log transform of odd ratio. Okay, the log of odd ratio is actually the logistic regression model that we're actually talking about. Okay, so that is why you have this here. So this is, you're going to write the log of odd ratio is now equal to the model. Look at that. So we call this log odds. Okay, we call that log odds. Okay, look at that. That's what we call log odds, because you know why? This itself is an odd. That is an odds, right? This that's an odds. Okay, and the log of that, that's why it is called log odds. Okay, so I want to tell you that logistic regression, we have it in different form. Okay, we have it in logit form. Okay, in logit form, the logistic regression in logit form, this is it. Okay, and we can also have it in probability form. Okay, I'm still gonna show you how the probability form of logistic regression is actually gonna be. Okay, so that is a model. Okay, right now, and this is the transformation that I just explained right now. Okay, that is the transformation that I just explained right now, that are called the logit function. Okay, now I actually told you the other time we got two formats of logistic regression model. And in exam, I can ask you any of the formats, okay, and I can ask you to state the two formats at the same time. Okay, now this is a logit form. Okay, that is a logit form, and this is a probability form. Okay, and how do we get the probability form? If you solve for expected value of y given s equal to that, from here, if you solve for that, it's actually going to give you this. Okay, you can try and solve for that. Okay, it's going to give you that. But you know what? Both of these, okay, both of these, they are actually population logistic regression model. Okay, they are actually, but because we're going to be fixing our model to data set, so what we're actually going to use, we're going to be using a fitted model. They want to have a cap. You get it now? So this is a fitted model in logit form, and this is a fitted model in probability form. Okay, I told you we have two formats for logistic regression. Okay, we have the one in probability form, and we have the one in logit form. Okay, so please take note of the two. We have one in logit form, we have another one in probability form. So those are the two formats. Okay, those are the two formats. In other word, the one that is the probability, okay, if you take a look at that one, okay, we can basically use y cap to represent that. So if I use a y cap to represent that, it means I can just have log of y cap divided by 1 minus y cap equal to beta naught cap plus beta 1 cap. Okay, can actually have that. Take a look at that. Okay, I can actually have that. Okay, when you take a look at what I have right now, I think I've already showed you how you know um you know the logistic regression in logit form and in probability form. And what I'm just trying to show you right now is when you solve, how do we derive the probability form from the logit form. Okay, you only need to solve for that. Okay, that's what we're doing right now, and that we actually, that's what I'm doing, and that will lead you to to the probability form. So what I'm going to show you right now is basically how to go from logit form of logistic regression to the probability form, and what we are actually solving for, okay, we are actually solving for expected value of y given x equal to that. That's exactly what we're solving for. Okay, so that is the way, and that's what I'm trying to show you right now. Take a look at that. Can you guys confirm again if you guys are still hearing me clearly?
Yes,
Okay, is there anyone who need clarification on how to derive the probability form of a logistic regression model from the logit form that I'm showing you right now? Is there anyone who need clarification on that?
I don't think so, no.
I understand.
Okay, thank you so much. Okay, um, I'm gonna move to the next one right now. Actually, the next thing that I want to talk about, since I've walked you through the theoretical development of logistic regression model, the next thing I want to do now is uh, how do we actually implement the logistic regression coding out if I have a data set. Okay, that's what I want to show you right now. Okay, there's something I wanted to pay attention to. In the code for logistic regression, we don't use LM, but we use GLM. Okay, what is it? Some of you may be wondering, what is the meaning of GLM? Logistic regression is a generalization of linear regression, and the GLM means generalized linear model. Okay, that's what GLM means, generalized linear model. So what that means is more or less like, okay, a generalization of a linear model. Okay, so in the R code, you're actually going to write GLM, and when you write GLM, you need to indicate family equal to binomial. If you don't indicate family equal to binomial, let's say for instance you remove this one, and even though you put GLM, it's going to give you a linear regression results. I'm going to say that again. Even if you put GLM and you decided not to indicate family equal to binomial, the kind of result you're going to have will not be different from the linear regression results. Okay, so you got to make sure you put family equal to binomial. Okay, now this is the output that you're actually going to have. It is similar to the linear regression output, but you know what? I wanted to take note of this right now. Okay, I want to focus my screen right now. You're actually going to see the difference. Okay, in linear regression, you are not going to see a z value in linear regression. What you're going to see in linear regression is t value. Okay, if you check what we've been doing before, and also check the p value. Okay, the p-value that you're going to see in linear regression is actually going to be t. Okay, so please watch out for that. Okay, that is one of the difference between that. Now if you take a look at the estimate right here, the estimates here,
Sorry,
they
can
okay.
can you repeat that? So the z value is actually the t value in this case.
Okay, yeah, if you take a look at the z, what you see here, in this column, when you run linear regression, it is going to be t value. Okay, in the case of linear regression, and this side will be probability associated with the t. Okay, so that is the difference between the linear regression output and logistic regression output. Okay, the logistic regression output will be, you actually going to see z value instead of t value. Does that, have I answered your question?
Yes, thank you.
You're welcome. So I want you to pay attention. I can give you something like this in exam, and I can ask you, what kind of regression output is that? Is it a linear regression output or a logistic regression output? Of course, the correct answer is going to be logistic regression output, because uh, in logistic regression output, we have a z value. Okay, we have that. That's what we have in logistic regression output. Okay, now another thing I want you to pay attention to right now. If you look at the estimate that we have right here, we call those estimates log odds. Okay, they are log odds estimates. Okay, we call them log odds estimates. Okay, and in a linear regression, we don't call them log odd estimates in the linear regression. I think you know that. In the linear regression, we call them estimates of regression parameters. Okay, that's what we call them, right? Okay, now if I have this output right now and I want to write a fitted logistic regression model, how am I going to write fitted logistic regression model? I told you the other time, if you want to write fitted logistic regression model, we have it in two formats. You say that you want to write the Logit form of logistic regression model, or you want to write the probability form of logistic regression model. Okay, now if you take a look at this guy now, that is a Logit form of logistic regression model. Now, I told you the other time, the log of y cap, okay, divided by 1 minus y cap, okay, is actually equal to beta naught cap, okay, plus beta 1 cap x, right? Now, your beta naught, okay, is the one that you pick from here, right? And your beta 1 is that one, right? Okay, when you try to put that in the model, now what I'm trying to tell you right now is that this guy here is the logit form of logistic regression model. Now, the probability form of that is this. Look at that. I told you we got two form. This is a logit form. Okay, this is a logit form, and this is a probability form. Okay, this is a probability form. Okay, so this is, I told you the other time when I started, there's a connection between between odd, okay, the log of odd and probability. And I told you the other time. So you may want to say that in the log odd form, in logit form, or we want to have it in probability form. Okay, so take a look at that. Okay, so I think I just show you now how you can actually, um, extract how you can write out the fitted model. Okay, how can we now make a prediction based on the fitted logistic regression model? If you really want to make a prediction, I will advise that you make use of the probabilistic form of the model, which is this guy here. Okay, because this is this guy now, what he's telling us now, we can actually predict the probability that oil rig will be damaged given the temperature. The temperature is X, right? The temperature is actually X, right? And the Y cap here means we actually want to predict the probability. Okay, what we're predicting right now is the chance of that particular whole ring being damaged, okay, given a particular temperature. Okay, so this can be, we can actually use that. Okay, in the prediction right now, we can have a model we can have a graph for that prediction. We are, at different temperature. Okay, at different temperature. Okay, when you plug in, different temperature right here, we're going to have different value for the probability that the oil will be damaged. And when we plot that, oh my God, what do you see now? This is very nice. This is not a straight line. And if you take a look at this is actually bounded within 0 and 1. Okay, you can see it is bounded within 0 and 1. Okay, the curve that we have now is actually bounded within 0 and 1, and which is a very good probabilistic representation of the relationship between the two variables under review. Take a look at that. Okay, with this model now, or with this now, when the temperature equal to 65, you can actually predict the probability that the O-ring will be damaged. Okay, you guys confirm again. If you guys are still hearing me clearly, are you guys still hearing me clearly?
Yep.
Yep.
Okay, so that is how we can actually use logistic regression to make prediction. Okay, so like I said, um, back to the launch day. Okay, on January 28, 1986, the year temperature, the year temperature was actually 31, Fahrenheit. And what is the expected probability? Okay, another thing I want to tell you now is the Y cap. It is not just probability, but it is expected probability because it's an average. Don't forget that this guy here is actually expected value of y, or given that that's equal to that. Okay, that is what it means. Okay, so that is what that means. So it's an expected average. Okay, so the expected value. So what I'm trying to talk about right now, I'm actually going to plug in that temperature, and I'm going to compute this one. And oh my God, that's a lot. That's 0.999. This is very close to one. So which means when temperature go down, okay, when temperature go down, okay, when temperature is very, very low, so at a low temperature, the probability that you're actually going to have O-ring damage is going to be very close to one. Okay, and take a look at that as you can actually uh, see. Okay, so that is what it means. Okay, when you plug in 31, okay, when you plug in 31, take a look at what you have. Okay, and so if that is what you have, then uh you can actually make an inference for that. So it means at any given temperature, okay, you can actually predict the probability of O-ring damage. And another thing I'm going to tell you is this. Okay, when the O-ring damage equal to one, let's go back to our characterization. At the beginning we actually just want to know, give me 1 second. I'm going to go back to our characterization now. When only when that when damage equal to one, if there's a only damage and a zero otherwise. So at the beginning we've coded damage to be one, and we coded zero to be not damage. Okay, so that is why when the probability is very close to one, then you are trying to say there's high chance of damage. Okay, when the probability is very close to zero, then there's a low chance of damage. So that's what we mean. Okay, so that is why we actually took that decision there. Okay, once again, this is a fitted model in Logit form, and this is the um, the fitted model in probability form. And of course, as you can see right here, this is actually
So can
okay.
I clarify?
Go ahead.
So y hat is the probability of damage of to the O-ring, correct?
Yeah, yeah. The is I think I will advise that you, because it has a cap, I will advise that you call it expected probability. Okay, expected probability of damage. Does that make sense now?
Okay. Okay,
Yeah,
so it's the expected probability of damage to the O-ring.
exactly,
Okay.
exactly. You are right. Now, right now we are using this example on something damage. Do you know that if a student apply for a student loan, it's either a student is given a loan or not, right? Now, in that situation, you're going to have predictor. Right now we're dealing with one predictor. We can also have situation where we have more than one predictor, and in that situation, we're going to call that multiple logistic. But what we're dealing with now, we're dealing with a simple logistic regression. The simple logistic regression is when you have one predictor. Okay, in this example, we just one the predictor is temperature. Okay, so when a student apply for a student loan, it's either the student is considered for loan or not. Okay, and if we consider a predictor like maybe credit history. Okay, I'm just assuming. Okay, so in that situation, your y cap is going to be the expected probability of you getting the loan. Okay, that would be the expected probability of you getting the loan. And the expected probability of getting the loan is actually going to be a function of some factors that they're going to put into consideration. Okay, if a student apply to graduate school, okay, if a student apply to graduate school, okay, it's either the student is considered for admission or not. Okay, the response variable in that situation is also there are two possible nature. Okay, it's either you are considered for admission or not, and that will now depends on some predictors. Maybe predictors like your the pedigree of your undergrad school, your GPA score, your GPA, and so on like that. Okay, so your y cap in that situation will actually be the expected probability of being given admission. Okay, that is it. So if you now look at what we have right now, we want to make some observation. Okay, we actually want to make some observation. Okay, and we want to make observation now. I think I talk about this, right? I talk about how you can interpret this model, the probability form. When I'm trying to say, okay, you talk about the expected probability, okay, expected probability, okay, of the characteristics of interest, right? Now, how do we interpret this guy here, the one in Logit form, okay, the one in Logit form, okay? So how do we interpret that? If you want to interpret the one in Logit form, you're going to say the log of, okay, the log of the expected probability, okay, of securing of the damage, okay, to the to the probability of no damage. Okay, now take a look at the interpretation right here. When the temperature increases, okay, when the temperature increases, okay, now I'm trying to interpret this model right now. I'm trying to interpret this model right now. When the temperature X increases, okay, the expected log, look at that, look at what I said, expected log odds. When I say log odds, I'm trying to say the log of the ratio of this, okay, the expected log odds, okay, of having, okay, whole ring damage, okay, will decrease, okay. Why do I say it's actually going to decrease? How do I know that? How do I know decrease? Because there's a negative here. Can you guys see that? Because of the negative here, that was why I say decrease. If there's a positive here, I'm actually going to say increase. But because of the fact there's a negative right here, I'm actually going to say decrease. Okay. Now, you're using the Logit form. Okay, this is how you're going to interpret the Logit form. Okay, look at that. So when the temperature increases, okay, the expected, look at the word, you got to put expected, okay, the expected log odds of having O-ring damage will decrease, okay. So take a look at that, okay. And if that occur, okay, when the temperature increases, okay, the expected odds, there's a difference between log odds, okay, and the odd itself. I'm going to tell you now, this is odd, that is all. And this the whole thing is log odds. There's a difference between the two. Okay. Now, but you know what? Whatever that happened to log odds is the same thing as is also going to happen to the odds. Okay, there's a decrease here. This is also going to be decrease. Take a look at that. Okay, so when the temperature increases, the expected odds of having now some of you, if you want to find the expected odd, we're going to find the expected odd from the log odd. What am I going to do? Now the expected odd is going to look like this. Exponential of that. When the log travel to both to the other side. Did you see that now? That's what you're going to have. Now this is odd right now. If I want to get the odd, okay, I'm going to take the anti-log of both sides, and that's going to be exponential at the other hand. Okay, so that is odd now. Okay, did you see that now? So that is what I'm trying to say here. Look at that. Odds is different from log odds. Okay. And you know what? The same decrease, they're always going to be in the same direction. They're going to be in the same direction. Okay. If I also want to interpret that of probability now, you can want to interpret the probability form of the model, it's still going to be the same. Okay. It's still going to be the same. Okay. So if you take a look at that, I'm still going to say when the temperature increases, the expected probability of having a O-ring damage will decrease. Okay. And that was why I said, look at that. I said logod, odds, probability all go in the same direction. Okay. Decrease, decrease, decrease. If they're going to be increased, they're going to be increase, increase, increase. Please take notes. Okay. They're always going to be in the same direction. Okay, let's confirm again. If you guys are still hearing me clearly,
Yep.
Yep.
okay, thank you so much. Thank you for confirming that. Now, this is going to be the end of the lecture for part one. I know I got two materials today that I actually uh, want to walk you guys through. Okay, give me 1 second. I'm actually going to stop my share, then I'm going to share the second material of the day. Okay, before I go into the second material of the day, can you tell me what is your experience like today in this material, the material we just ended? If your experience is great, I need you to say yes or you comment yes. If you really
Yes.
want, okay,
Yes.
thank you so much. Okay, I want to welcome everyone to the second, uh, the topic of the day. We are still on logistic regression, but this is going to be part two of what we started. Okay, it's going to be part two. Okay, um, I think I've really explained. There's a difference between linear regression and logistic regression. You take a look at this side. This is linear regression, right? Take a look at that. And this is the logistic regression. And I said, of course, the difference between them is just the nature of the response variable. In linear regression, the response variable is quantitative and continuous. Okay, and of course, in the logistic regression, the response variable is binary. Okay, binary means it has two nature, two possible nature. Okay, which we actually denote with 0 or 1. Okay, take a look at that. Okay, there's another thing I want to talk about. I think it's gonna be advisable to look at the three things in logistic regression that are very, very important: the probability, the odds, and the log odds. You remember in the last material, I said the three of them, they're going to be in the same direction. Okay, I think you know that. Can we have a way to distinguish the three of them using formula? Can we also look at the range? Okay, can we look at their range? Because by the time we are actually making inference, we're going to be making inference on probability, we're going to be making inference on odds, we're also going to be making inference on log odds. Okay, for probability, of course, I told you the other time, that is expected value of y of the response given the predictor equal to that, and that can only occur in the range of 0 to 1. Okay, that would be from a range of 0 to 1. Take a look at that. That's a close one, right? That's a close one, right? Okay, for the odds, of course, it's basically the ratio of that probability of success or the probability of failure. And let me tell you, the range of odd is from 0 to positive infinity. Take a look at that. It's going to be from 0 to positive infinity. Okay, when I talk about log odds, when I talk about log odds, of course, this is what I mean. And of course, the range. It's going to be from negative infinity to positive infinity. Okay, I think I'm just trying to show you this right now. That will guide you if you want to make interpretation. Okay, if you want to make interpretation about probability, of course, we're trying to show you about how the range is going to be when you're making, you know, inference about odds. Okay, that is a range for logos. That is a range. Okay. You remember the other time I walked you through an example that I call where a rocket was launched and it was ruptured, and they investigated to see what was the role temperature play in that. And then when we make an attempt to fit a linear regression, look at that. When we fit a linear regression, we obtain the beta null, we obtain the beta one. But you know what? This model cannot be trusted. Okay, and you know what? When you make an attempt to make a prediction about the expected probability of damage, is going to go over the range of 0 and 1. Okay, there's possibility you could get a negative value. There's a possibility you get a value greater than 1, and that doesn't really make sense at all. Okay, so, and that was why we said, okay, what is going to do the job is to use a logistic regression model. Using a logistic regression model, of course, you're actually going to have, what you're going to have, we within the 0 and 1 interval. Okay, so you can look at that now. And of course, the other time I said you're actually going to have two form of fitted logistic regression model. You're going to have the one that is in probability form, and you're going to have the one that is in Logit form. So take a look at that. Okay. And of course, I actually walk you through how you're going to make decision, how you're going to interpret the model. For instance, if you want to interpret the logos, you're actually going to say the expected. Please don't forget, you got to make sure you put expected. Okay, the expected is more or less, on average. Okay, that's what we mean. So the expected log of having O-ring damage will decrease. How do I know that? Because of the negative that we have. And of course, that of the expected odd, we also going to also, this is what I showed you the other time, that if I want to find expected odd, of course, if this is the log of that, then the log coming to the other side is going to be exponential. Okay, take a look at that. So the exponentiation of the log odd will give you odd. I'm going to say that again. The exponentiation, okay, of the log odd will actually give you odd. Okay, this is a odd, and of course also going to be decreased. And not only that, the probability will also move in the same direction. I think I said this in the last material. Okay, now I'm bringing this thing again. Three important things. Okay, look at that. As well as uh, regression, logistic regression model is concerned, we normally want to interpret three important things. Okay, the log odds, the odds, and the probability. Please take note of this. Okay, those are the three important things that we always want to interpret. Okay, those are the three important things that we always want to interpret. And I actually give you the range of this one. Okay, the range of probability is from 0 to 1. Okay, I give you the range of odd from 0 to infinity, and I give you the range of log odd, negative infinity to positive infinity. Okay, take note of the three. So this is a way, because an examiner can ask you to give a fitted model of logistic regression in logit form, in odd form, or in probability form. So take a look at that. And what I provided right now here, okay, so and before, I think I've told you how to interpret this. Okay, I think I've walked you through how to interpret all of that. They're going to move in the same direction. Of course, they're going to move in negative direction. Okay, there's something I want to talk about right now. when the temperature increase by 1 degree, okay, when the temperature go up by 1 degree, how does that really affect the log odds? Okay, now the log odds of having O-ring damage is expected to decrease, and we know that. We know it's going to decrease, okay, because of the fact that we got a negative right here. But the question now is, by what magnitude is it going to increase? And that's what I want to tell you now, which is going to be the additional thing. Okay, so take a look at that. By a 0.232, can you see that now? By a 0.232. Okay, and where did I get that from? It's actually from here. Look at that. Okay, so if I want to use this particular value here, then it means I'm talking about log odds. Okay, it means I'm talking about log odd. Now let's see how the odd is going to be. Okay, the odd of having a ring damage is expected to decrease by 20.7%. How do I know that? How do I know that? Okay, now what you're going to do, you're going to take the exponentiation. You're going to take, what is the exponential? Raised to the power minus 0.232. Okay, exponential raised to the power that. You see that? Exponential raised to the power that, then minus 1, then the absolute value. So what I'm trying to say now is going to be exponential raised to the power minus 0.232, okay, minus 1, okay, in absolute term. You see that now? And that's exactly what you're going to have. So when you do that, it's going to give you this result. So please take notes, okay? So when you want to uh, obtain that, that's exactly what you're going to do. You're going to use this. So did you see now? So that's exactly what you're going to do. Okay, you're always going to make sure your beta one is actually this guy here, right? You see that now? So you're going to take the exponential of that, okay? And when you take the exponential of that, you're going to subtract 1, okay? Then you're going to take the absolute value. The essence of taking the absolute value is for you to get a positive result, okay? It's for you to get a positive result. Okay, now, and some of you may be wondering, how is it that this is actually what we're using? Okay, I'm actually going to demonstrate that to you right now, and you're actually going to see. Okay, now we said when the temperature increases by 1 degree, right? Okay, let's get started. You're going to see that, in odd form, this is what we have in odd form, right? Okay, now I want us to have two odds. Okay, I want us to have two odds. Okay, in the first odd is this guy. I have x1. Can you see that now? In the second odd, I have x2. Okay, and you know what? If the pressure go from is increased by 1, then it means maybe when I have x1 here before, therefore x2 is going to be x1 plus 1. Okay, the x1 plus 1 means, oh, it's going to go up by 1, right? Going to go up by 1, right? Okay, now let us now look at the ratio of that particular horde right now. Okay, the ratio of the two hordes. Okay, the second horde divided by the first horde is what I have here, right? And the temperature going up by 1 means my x2 equal x1 plus 1, right? And you see that now? Then I'm going to plug in this one into wherever I see x2, and that is why I have this. Can you see that now? So all what I'm just going to do is to simplify. I want to simplify this. Okay, if you want to simplify this, you're going to say, oh, minus of 0.232 times x1 is going to be this guy, right? And this guy multiplied by 1, I'm going to have this, right? So I'm going to have the whole of this divided by that. Okay, you see that now? Now, when I have that, I can actually split this into exponential carrying this and exponential raised to power that. Look at that. That's what I have here, right? Okay, and you know what? This guy here is going to cancel that guy there, right? I have this guy now, which is this. And what is the exponential raised by that? I'm actually going to get a 0.793. Okay. Now, if I get a 0.793 right now, what does that mean? What that means is that if you want to know the change, okay, if you want to know the change, that has occurred, okay, then you're going to do is going to be the new, okay, odd minus the old odd divided by old odd. I mean, the odd, or odd for the second one minus the odd of the first one divided by odd of the first one. You remember how we compute the percentage change? You remember how we do that? Okay. Now, that is what I actually want to do right here. Okay. So what I'm trying to talk about right now is that if I want to do that, it's more or less like subtracting, one from this. Okay. It's going to be this guy. Okay. Minus one. Okay. How do I know? Now take a look at this. I'm going to express that for you. It is written as odds. Okay. Divided by this guy here. Okay. Minus odds. Okay, minus ox 1, that one divided by, I think you see that, right? Okay, if I want to rewrite this, and this is going to be this, okay, minus 1, and this is this guy here. It's what we just derived right now. Then minus 1, then we have this guy now. Okay, so why do we, and I told you, of course, you are not surprised with the negative because we'll be talking about decrease. Okay, the beta one was negative, right? I think you know that. So what I'm trying to tell you right now is that when you now take the absolute value of this, okay, and you multiply by 100, that would be 20.7% that I talk about. Okay, that is 20.7% that I talk about the other time. I'm going to show you now, and that was how we said it's going to be that. Look at that. But you know what? You don't need to do all this. You don't need to go, or you don't need to do all this, or what you just need to do. This is the formula. Just use that one. Okay? Just use that one. Okay? And don't forget the exponential is power beta 1 is the ratio of odd that I talked about the other time. Okay? That is the exponential is power beta 1. Okay, that you plug in there. Okay, take note of that. Okay. I want to walk you through another example right now. But this time around, we want to look at the relationship between smoking and mortality. Okay, what is the relationship between smoking and mortality? That's what I want to show you right now. That's another application of logistic regression. Okay, okay, you guys confirm again. If you guys are still hearing me clearly,
Yep.
Yep.
okay, thank you so much. Thank you for confirming that. Let's look at this story. Women were interviewed about whether they smoke. Okay, and the outcome variable record whether each woman was still alive 20 years later. Okay, during the follow-up study. Okay, now we have about 1,314 cases altogether in this data set, but right now I'm only showing 106. Okay, you know the response, this is the outcome. uh, One is coded as alive. I know we coded alive as 1, and we coded dead as 0. And of course, if you take a look at this person, is age 23. Okay. She smokes and is alive. Look at this person, is age 18. She smokes and is alive. But look at this person, age 71. Okay. She smokes. Okay. And is not alive. She's dead. So we have a lot of that. Okay. So, for instance, like this one now, for instance, I said a case study was 71 years old at the time of the interview, okay? And 20 years later, she was no longer alive, okay? It means at the, this is a follow-up study when she was age of 51, okay? She was interviewed, okay? And she said, oh, I smoke. And you know what? 20 years later, okay, we realized that she was no longer alive. Now, the question now is, what is the effect of smoking on this outcome? Or is it just age? Or, we want to know. So that is the essence of this study. And that was why I said, okay, you know what? We're going to fit a logistic regression model to predict the outcome, okay, based on smoking status and the age at the first interview, okay, at the age, okay, at first interview. So that's what we want to do now. Um, you know, you remember when we're dealing with the multiple linear regression, where we consider more than one predictor at a time. We're also going to do that in logistic regression model, where we can actually look at the effect of more than one predictor at a time. Okay. Now, take a look at what I have here. This is like plotting the outcome against the age. Okay. And, whether they smoke or not. Okay. Take a look at that. That is that. How are we going to do this in R? Okay. If I have my data set right now, how am I going to, implement this in R? Okay, now I wanted to take note of this code right now. Okay, don't forget I'm going to write GLM. Okay, and you know what the outcome here is just, alive or dead. This is the response variable. And of course, I'm looking at the effect of age. At the same time, I'm looking at the effect of whether the person smoke or not. Okay, so which means in this study, we are looking at the role, we're looking at the effects of age and the effects of whether somebody smoke or not, okay, on the probability of that person being alive. Okay, that is the essence. Okay, this is the result, this is the output, that is the regression output. I think you know the reason why there's a smoker, yes, right? Okay, can somebody remind me, why do we have a smoker yes in this output? Can somebody tell me? For extra credit, why do we have a smoker yes in the outputs? Can somebody tell me?
I do not know.
Oh, okay. Uh,
Is
okay.
it because of we have it's a binomial um function, so we have the no, so we have the no and yes, and it determines whether it's like 0 and 1.
Exactly. Now, for you to get your full point now, which one is coded one and which one is coded zero? Is it smoker yes? That is, or smoker no?
So smoker yes would be coded as would it be coded as 0, and then smoker no would be coded as 1.
Are you sure? I'm gonna
Oh,
tell you now. Like,
uh,
anyway, you try.
um,
You try. You know,
well, would
okay.
it be would it
Uh,
be the opposite? Since if it
yeah.
was smoker yes, then you would plug in 0 for
Okay.
the okay.
I'm still gonna give you extra credit, but let me tell you this. I told you the other time that the one you see in the regression output is the one that is actually coded one. Okay. So what are you seeing in the regression output right now? It is smoker yes. So therefore, it means yes is one and no is zero. Okay. So if you want to know the one arrow actually coded as one, okay, then you have to look at the one that is reported in the regression output. Does that make sense to you right now?
Yes, thank you.
You're welcome. Okay. Now, so take a look at that now. So based on this, I can ask you to write a fitted regression model. But the fitted regression model that I'm writing here is a logit form. Okay. I can ask you to write the logit form. You can write the probability form, and this is the log odd form, right? You can also write the odd form as well, right? Okay, so take a look at that. So which means I'm actually using the combination of that, right? Look at that. Okay, that's what you can see right now. Okay. Um, We have it in the Logit form right now, and the question now is, how can we interpret this? Okay, like I said, you can have it in Logit form, you can have it in probability form, okay? You can also have it in odd form, okay? The Logit form is the same thing as log odd form. So right now, I'm actually presenting that in log odd form, which is we call Logit form. Take a look at that. Okay, now how can we interpret this model right now? Because well, when you fit a model, uh, we're actually going to have a way to interpret the model. Okay, and if we want to interpret the model, we got to interpret the intercepts, the slopes and the like. Okay, now take a look at this. Let's start with the age. We want to interpret the age now. And this is what you're going to say. If you want to interpret the age, don't forget that we also adjust. We adjust for the smoking status. Okay, so you're gonna say holding smoking status at constant. Okay, when age. Okay, when age, focusing on age. When age increases by 1 year. Okay, the unit of age is in year, right? Then the horde of survivor, look at that, hordes. Okay. If I want to talk about hordes of survivor, the odds of survivor is expected to decrease. How do I get 11%? Don't forget, you got to do that. Okay. -1. You remember that we did the other time, which is exponential raised to power beta 1. Okay. -1. Okay. And you're going to take the absolute value of that, and that will give you 0.11. Okay, and you're going to multiply 0.11 by 100. Okay, when you multiply 0 by 11 by 100, that's going to give you 11%. Take a look at that. Okay, so holding smoking status at constant now, when age increases by 1 year, the odds of survivor is expected to decrease by 11%. That's what we mean. Okay, that's how that is interpreted. Okay. Now, how do we now interpret the categorical predictor variable? The categorical predictor variable, the smoking status. You're also going to say holding age at constant. Don't forget, okay, age is also a predictor in the model. So holding age constant, when compared to the non-smokers. Now, take a look at that. Look at what I said. When compared to non-smokers. Okay, why do I say when compare to non-smokers? Because the predictor variable that I actually want to interpret right now is categorical. And when compare, it means if you look at my regression output, you saw a smoker, yes, right? Okay, then it means we actually want to compare the smoker, yes, to what? To non-smoker. That is what it means. Okay, to non-smoker. And that was why we said when compared to the non-smokers, the odds of survival for smokers is expected to decrease by 18%. How do I know that? Of course, I'm actually going to use the exponential raised to power minus beta 2 minus 1 and take the absolute value. Okay, what is the slope for smokers? You're going to go up. The smoke, the slope for smoker is actually that. Look at that. Can you see that now? And that is what you see in the model right here. Okay, you're going to take the exponential of that. Okay, you're going to take exponentiation of that, then subtract 1 from that. Whatever you get, you take the absolute value, then you multiply by 100. Okay, and that would be 18%. Now we talk about. Okay, so that is how we come about that. Okay. Okay, so which curve represent the smoker group? Okay, now take a look at what I have right now. Okay, we have we fitted a model, and this is a curve right now. We have a non-smoker zone. We got a smoker zone. Okay, I can actually ask a question like that. Okay, and you'll be able to know which one. Okay, and that was why I said holding age constant. Okay, the smokers have a smaller log odds for survivor. I'm going to say that again. Holding age constant. Okay? Provided, your age, it's being held at constant. Okay? Then the smokers, okay, actually have a smaller log odds for survivor than smokers. Okay? Take a look at that. Okay? So the smokers have a smaller log odd for survivor than non-smokers. Okay? It's, take a look at that. So therefore, what we mean, what we're trying to say in essence is that the smokers have a smaller probability for survivor than non-smoker. That's what we mean. But before we can say that, we have to hold age at constant. Okay? Take a look at that. Okay? And that's what we mean. And if you really want to figure out, like, okay, can I have a way to predict for a particular person who is age 60, which is exactly what I'm using the graph here to do. Okay? For 60, can we actually predict the probability that the person is going to survive? Stuff like that. You can use a model to do that. Since uh, you already have your model. This is your model. Okay? Now, if that is your model, okay, and you actually want to predict, okay, for age 60, okay, all you just need to do, okay, is to plug in the value, and then you're going to plug in one here. Okay, why are you plugging one? Maybe okay, can we have a way to predict the log? Okay, not only the log odd ratio, can we also predict the probability of somebody who smoke? Okay, this person smoke and and her age is 60. But that's why I'm going to plug in one here, and I'm going to plug in 60 here. Then I'm going to compute that. Okay, so if I want to predict for somebody who did not smoke, okay, I'm going to put the age of the person here, and I'm going to put 0 here. Okay, and I'm going to compute. But right now, what I want to compute is for somebody who smoke, okay, and the age is 60. That's what I'm doing now. And what is the log? The log odd give is 0.2. Okay, the log odd give is 0.2. So which means you are comparing a 0.2 to 1, right? It's 0.2 to 1. Which one is smaller? It means the one for smoker. Okay, and if you want to know in probability form, okay, if you really want to know in probability form, you can solve for y cap. Okay, you can solve for that, and the probability is going to be 0.55. Look at that. It's kind of dicey. Okay, somebody who is at age 60 and smoke, based on this data, kind of dicey. And what I'm doing now is somebody at age 60 and the person do not smoke. Okay, you can see that the log odd here is greater than the log odd here. Look at that. The log odd here is greater than, of course, the probability is also, if we go ahead and compute the probability, look at that. The probability for non-smoker is going to be higher than that of the smoker. Look at that. That I'm talking about the probability of being alive. That's what we mean. Okay. Is there anyone who want to ask question? As this is where I'm actually going to stop for today. Is there anyone
I think
who want
I'm
to?
good.
Okay.
Yeah, I understand the material for today. I actually had one question about the material from the last two lectures. Um,
Okay.
so I'm kind of confused about the AIC and BIC. Can you kind of review that and explain why we need to use both of them and kind of what they represent?
Thank you so much. That's a very good question. If I hear you clearly, you are trying to